A warm welcome to this lecture on the subject of wavelets and multirate digital signal processing. We build in this lecture a very important principle. In fact, in some senses, the principle that lies at the heart of the subject of wavelets and time frequency methods, namely the uncertainty principle. Therefore, as you note, today we shall devote the whole lecture to a discussion of the uncertainty principle, laying the foundation of what uncertainty means first, and then proceeding to obtain certain numerical bounds on confinement in two domains simultaneously. Let me first give an informal or a diffused non-formal introduction to the idea of containment. Well, we did a little bit of that yesterday in the previous lecture, but what I intend to do now is to say a little more in terms of formality and then proceed to write down the mathematical relationships or definitions. Recall that we said that there is of course, a very tight or a very strong kind of notion of confinement. That would ask that you have compact support in both domains, time and frequency. The function must be non-zero strictly over a finite interval of the real axis and must be non-zero strictly over a finite interval of the real axis in the frequency domain as well. So, both in time and in frequency, you demand that the function be non-zero only over a finite part of the independent variable or the real axis. This is a very strong demand, and of course, yesterday we mentioned that it cannot be met ever. And in fact, I also hinted at the idea behind the proof. It related to the fact that if you noted that the function was finitely supported, compactly supported on the real axis, there were certain properties of that function, specifically the existence of an infinite number of derivatives, which made it impossible for that function to be compactly supported or non-zero only on a finite interval of the independent variable in the natural domain. Natural domain can mean time, can mean space, whatever. Anyway, this was what we called the strong version of containment, and we said that this of course was not possible, but we had asked whether a weaker notion of containment could be admitted. Namely, we do not insist that the function be strictly non-zero over a finite interval, but that most of its energy, most of its content, so to speak, in some sense, be on a finite interval of the independent variable, which indexes it. And simultaneously, in the transform domain, in the frequency domain, we insist that most of the content be in a finite interval of the frequency axis. This seems like a more reasonable requirement, and to a certain extent this requirement can be met. And as I said, to give a diffused or a non-formal presentation of how it can be met, I shall begin this whole discussion by saying that we are finally going to come out with certain bounds on how much you can contain in the two domains simultaneously. So, there are several steps to reach this destination. The first step is to put down in a non-diffused, in a formal way, what you mean by containment. What do you mean by most of the content being in a certain finite range? And we had also hinted at the approach that we would take to do this briefly in the previous lecture. We had said that there are two ways of looking at it. You could think of the magnitude squared of the function and the magnitude squared of the Fourier transform as a one dimensional object. And then you could talk about the center of that object, center of mass if you like. You could talk about the spread of the object around the center of mass by using the notion of radius of gyration. Or if you prefer to speak in the language of probability densities, then you could employ the idea of a density built from the squared magnitude of the function and another density built from the squared magnitude of the Fourier transform. You could then look at the mean of these densities and the variance of these densities, and the variances are indicative of the spread. So, this was a non-formal introduction. Now, we need to formalize it, and that is what we shall do precisely to begin with. Put down a formal definition, a formal explanation of the idea of spread. Now, of course, we have to define the domain in which we are going to work. We are going to work in L2R, we have agreed to that. It is always going to be the space of square integrable functions. In fact, I must mention that sometimes we are actually going to work in the intersection of the space of square integrable functions and absolutely integrable functions. To be on the safe side, let us put down that requirement right now, and let us put down the tightest of the requirements, namely that the function belong to the intersection of these two. So, the context consider a function, let us say x of t, which belongs to the intersection of L2R and L1R. Which means it is both square integrable and absolutely integrable. I think we should note that. All right. Now, because the function belongs to L2R, we are sure that its Fourier transform also belongs to L2R. So, let us x t have the Fourier transform x cap capital omega, and we know that capital X, x cap of capital omega belongs to L2R as well. So, we first define a density or a one dimensional mass, if you would like to call it that. We know that both x t and x cap omega are square integrable, and therefore, if we take the magnitude squared of x t and the magnitude squared of x cap omega, they would enclose a finite area under them. In fact, the two areas would be essentially the same, but for a factor of 2 pi. Again, if we chose to do away with angular frequency and used Hertz frequency, that 2 pi factor would also go away. Anyway, what we are saying is mod x t squared integrated from minus to plus infinity is finite. Let us in fact use the standard notation for this. The norm of x in L2 R the whole squared, and therefore define a density P x given by mod x t squared divided by the norm again squared. Now, a few remarks, and in fact, we should write them down one by one. P x t as we have defined it, namely mod x t squared by the norm in L2 R of x the whole squared is a probability density. Why do we say this? Well, because of the following reasons. Let us list them one by one. Number 1, P x t is greater than or equal to 0 for all t. It is a density in t, of course. So, you may think of t as a random variable, and this is the density on that. The integral over all t of P x t is easily seen to be 1 from the definition. Essentially, the integral of P x t over all t would in the numerator again have the L2 norm of the function x, and of course, the denominator is indeed the L2 norm of the function x, of course, both squared, the numerator and denominator, and therefore, they would cancel out to give 1. Similarly, let us define a density in the Fourier domain, in the angular frequency domain. And there we shall write P x cap as a function of omega to be mod x cap omega squared divided by the norm of x cap squared. Here again we are assured of the denominator being finite because of the L2 R business. So, again we shall for completeness and formalism note that this is a probability density. P x cap omega is also a probability density. Indeed, P x cap omega is greater than or equal to 0 for all omega. It is a density in omega. And the integral over all omega from minus to plus infinity of P x cap is 1. That is also easy to see by very definition. Now, we have taken the probability density perspective, but we could as well take the so called one dimensional mass perspective, and let me also note that. One could also take a one dimensional mass perspective. That is, we could think of P x t as a 1D mass in T. And similarly, you could think of P x cap omega as a one dimensional mass in omega. So, what I am saying is all of us or all the objects around us are masses in 3-dimensional space. So, here we have a simplified situation. You have a mass in 1-dimensional space. That 1-dimensional space can be the space of T or the space of capital omega. Similarly, as I said, P x cap omega is a 1-dimensional mass.